Hi, our team will be discussing the methods used for computing absorbed dose of radiation from CT imaging. We will touch on current methods, simulation models, and future implications over the course of this presentation. I'm Ji Chen, and my teammates are Huilong and Yuxuan. First, I would like to read the term effective dose E. Under the activity A, the patient will experience exposure X. Radiation will be absorbed, and equivalent radiation is affected by the winning factor WR, and total radiation of certain tissue or organ will be modified by the WT, and is called effective dose. This term is commonly used in hospital standards, and both gray and silver are units of radiation, which is the joules per kilograms. The formula for calculating effective dose is illustrated by the formula. The DTR is the absorbed dose average over the tissue or organ with given radiation R, and HT is the equivalent dose of tissue or organ. The calculation of HT is also different with sex, but we are not going to that field for simplification. The table of winning factor of tissue WT and winning factor of radiation WR are in Appendix 1. For CT, the WR is equal to 1, and the WP varies based on organ or tissues that is under the CT scan. The sum of WT is equal to 1, which indicates the whole body. Next, I would like to introduce an approximation model for CT. CTDI is CT dose index, and DLP is the dose loss product, as shown in the figure. The CTDI is average dose in C direction at a given point. The DLP is the total exposure during the acquisition of the image. DLP is equal to the distance times CTDI, and table of the K factor are placed in Appendix 2, and it will vary based on the ages. CTDI can be involved with a lot of terms. For example, CTDI 100, CTDI W, and CTDI volume. In general, as shown in the left side of the slide, CTDI or specifically CTDI 100 is amount of radiation of one slice of body over the scan. CTDI W is weight average of center and peripheral of CTDI 100, as there are more dose at peripheral region compared with center, as illustrated in the formula on the right side. The CTI volume is the volume of the total dose that relates with pitch. The pitch is related to the length of the beam, the rotation of the machine, and the movement of patient. Generally speaking, higher pitch equals lower dose as less overlapping.
All right, so now I'll be discussing the Monte Carlo simulations. The Monte Carlo simulation is a way of using random numbers to generate the inherent probability distribution of the different changing variables that would exist in the real generation of radiation particles. Notably, Monte Carlo simulation of radiation stems from atomic and nuclear physics and are typically very precise. However, the equivalent methods used in radiology is typically cut down to speed up the processing time. However, it is still by far the most robust and precise method of calculating radiation dosage. First, let's discuss the beam. There are two methods of generating such a beam. The first is to simulate the beam itself based on detailed knowledge of the device that is being used or previously collected analog data on the behavior of the beam from the emitter. As you can see on the left, it is possible to match the beam very closely to the real expected emissions from the system and then processed with a random process simulation with the exact same distributions. Another method is to simulate the beam from the first event, which is the photon hitting the anode, and increasing a beam by calculating the random possible emissions using formulas and the laws of physics. This is useful beyond just dosage calculations, such as for the design of the product, since some models are able to reflect the effective beam that might result from the varying shape of the anode. Following that, the next thing to consider is how to simulate the patient. This can be done largely with two methods, using voxels that simulate the various tissues of the patient, or to simulate an object of known quantity, such as a cylinder of water. Both methods are established and used in the field to varying degrees of pros and cons. In the case of simulating the patient with voxels, each voxel can be set to have different Hounsfield numbers from which the density and the type of material can be determined in relevance to the simulation. This can be very effective in creating an exact simulation of the person involved. However, this can be more compute consuming and not ideal if speed is extremely important to the situation at hand. Simulating with more known quantities, on the other hand, can be done rapidly and is very important because it is essential to calibrate the system. For the sake of accuracy, and of course not to put anyone at risk, this is typically done with a body of water, but can also be done with human body phantoms, which are these cylinders with homogeneous Hounsfield numbers that can have inserts to simulate different parts of the body. These are easy to simulate and can give results very close to one simulated with exact voxels. In the case of radiology, the process would now be to simulate the random radiation results that come from the photons or electrons. They will be affected by the different layers depending on how complex the simulation is. Some simulation processes can even showcase gradients that appear through the same layer of tissue. However, simulations of this complexity is unnecessary for medical imaging purposes, since generally you're only looking for overall dosage. Now, I will showcase a software in the field that is openly available to run basic simulations that is also much faster than trying to calculate a precise number by hand. Since it is quite difficult to write a simulation in MATLAB or otherwise within 2 weeks, this is the tool that we opted to showcase. This tool here is known as GMC-TDO-SPP, and it is a Monte Carlo simulation tool. This tool started development over almost 10 years ago and is extremely powerful, but also extremely fast. A 10-second exposure simulation takes less than 9 seconds of simulation time. As you can see here, by simulating the varying voxels with the different properties, we're able to get exact exposures, not just overall, but to each organ. These types of simulations nowadays can be written to each CT machine separately and customized depending on what the machine is primarily being used for.
While in the section, we'll focus on the deep dose estimation. It's a new technology that combines the dose calculation with deep neural networks. But first of all, let's come back to the old method. Monte Carlo simulation is pretty good. However, the computation time is an issue because of the computational complexity. It will take too much time to analyze the data. Of course, there are other faster ways, such as analytical approximations, but it would cause a reduced accuracy. So the high accuracy and high speed seem to be controversial. But deep dose estimation is a key to solving these problems. With the neural networks, we could use previous data to train the module and predict the dose description in light seconds. So the next slide shows the basic approach of the DDE method. There are two inputs. The first one is a reconstruction image, and the second one is fourth order dose estimation. In the fourth order dose estimation, we consider the energy from photoelectric effect and the single captain scattering. What's more, we will regard the body as equal to the water, so it could be background dose distribution. So we make it as a control group to make the module understand what is a big mass density tissue, such as bones. Finally, we use the reconstruction plus the fourth order dose distribution as an input signal to train and improve the module. So as the output dose distribution is shown on the left, the image D compared with the conventional method, the image C, we could see that the DDE had a similar accuracy, but could finish the process within only 214 milliseconds. From the perspective, DDE is a perfect method to satisfy our requirements. However, on the contrary, it has its own disadvantages. Displayed on the right, image error occur with the neural networks. In the example of the log image, at the point where the red narrow pin, such as this, it displays. So we can see that in the original one, it looked at branches, but in the predict one, he looked at combined together. So the neural network changed a feature of the lesson. We know that the different lessons correspond to the different attenuation of energy and show the different colors in the image. So the system will remember the arrow signal, and then it will affect the dose distribution as well.